three basic types of problems in algorithm. Yeah, so in this class, we need to learn three basic problem types. Okay, all right. First one, search type. Yeah, so we learned one last time. Second one, sort. Yeah, so today we will do our first sort. The third one, selection problem. Yeah. And this one is the simplest selection problem. All right. Yeah. So first, let me give you the question statement. Yeah. Our problem number 5. Find the minimum of an array. Yeah. Question. Given an array. Yeah. So arbitrary array. Here, if I do not say anything about if it is ordered or unordered, then we mean unordered. Okay? Yeah. If it is ordered, I have to say ordered. If I do not say anything, you assume it is unordered. Yeah. All right. Yeah, because sometimes students still ask me, ordered or unordered? Yeah. If you do not say the ordered word, by default it is unordered. Yeah. Now we need to find the index I such that A of I is the minimum of the array. Yeah. So that's the question statement. Very simple. Yeah. All right. First, the problem type, selection type. So what's the selection problem? Yeah, I will give you later soon. Yeah. A reference. Yeah. So now you can see we go back to section 2.3. Yeah. From now on, starting because today our 4th lecture, right? Yeah. The 3 lectures before today. So in order to let you do programming projects as early as possible, then I talked about some materials from later chapters. Yeah. Chapter 6, I pick one topic for our first programming project. Chapter 11, I pick another topic for our second programming project. Yeah. But after those 2 project preparations, so starting from today, I will pretty much follow the natural order of our textbook. Yeah. So we start from 2.3, so then we, follow the natural order. All right. Definition of the selection problem. Find the kth smallest element. K is some given integer. Yeah. Yeah. Could be 1, 2, 3, and so on. So find the kth smallest integer in a given array. That's the selection problem. Okay? Yeah. So here for our minimum problem, so you can see K is a special case, K equals 1. Yeah. And sometimes people call the rank. So this K number, people also call the rank equals 1. Yeah. The terminology. Yeah. All right. Then the maximum, yeah, K equals N, finding the maximum. Yeah. All right. Yeah. Later, we need to look at the, other special case. Yeah. For example, when K equals 2, so how to solve this selection problem. Yeah. And another one, special one, very important, finding the median. Finding the median. Okay? Yeah. Yeah. Also a special selection problem. Yeah. Then in chapter 4, Module 4, not Chapter 4. In Module 4, we will learn the general K problem, general selection problem. Yeah. But the general problem, I may not go to the details. Yeah. So I just talk about a little bit. Yeah. Because the detail, the solution, very complicated. Yeah. All right. Yeah. Let's look at the solution. The solution very simple. Here, let me quickly give you the solution. Yeah. All right. First, we do initialization. Initialize a variable we call the main. Its initial value is the value of the first element, A of 0. After that, then we do comparisons. So the general step, yeah, we compare the value in this main variable to the current array, A of I, the current array. Oh, sorry, current element in the array. Yeah. Then the condition, if main greater than A of I, then that means the value of the current element is smaller than the current value in the main variable. You should update the value in this main variable by A of I. Yeah. So because your goal, you want to find the smallest array element. Yeah. Otherwise, yeah, not smaller, then we go to the next iteration. Yeah. So compare main with the next array element A of I plus 1. Then see if we need to update main or not, until we reach the end of the array. After we finish comparison with all the remaining elements, then at the end we return the value in this main variable. That's the solution. Okay? The solution pretty straightforward. All right. So, but for the topic here, our main focus is not at the solution. Yeah. The solution is pretty simple. Our main focus is not at the solution. Yeah. Our main focus is another important question in algorithm. So that's the title of our part D. Optimality in algorithms. Optimality. Yeah. So here we need to do discussion on this optimality issue. Yeah. All right. So before we move to optimality topic, yeah, let me ask you this question. Based on our description of this whole solution, can you tell me how many comparisons do we need here? Yeah. The number of elements in this array n. So you need to use this n. So your answer should be in terms of n. Yeah. Yeah. So do you have an idea how many comparisons we need to do to find a solution? Based on our comparison steps from beginning to end. Yeah. Can anyone type a number in the chat area? Your answer? How many? So another counting problem. Yeah. Yeah. Good, great, yeah. 2 students give me the correct answer. N minus 1, not n. Yeah. So here, you should be very careful. Yeah. Because many students, those students could be easily give me the answer n minus n. It's very likely. Yeah. Can any of you, oh, sorry. Yeah, I need to, yeah, because I need to look at your message. Yeah. Oh, so I need to control. Okay. control the window. All right. Can any of you, Woodrow or Mitchell, any of you can explain why you give me n minus 1, not n? Why your answer is n minus 1, not n? Huh? Yeah.
Yeah, my thinking was it takes two different terms to make a comparison, so
Yeah.
the first comparison takes two.
All right. Yeah. Okay. I can see your view. Yeah. Yeah. Take 2, but here we use a mean variable. All right. This mean variable, then compare with each element. But the first initial value of the mean variable comes from the first element. That means, look at this initialization line. This line, we do not do any comparison, right? This line, we just do assignment operation. This is an assignment operation. It is not a comparison operation. So when we count the normal comparison, we do not count. We do not count this one, okay? Yeah. So for the first element, it doesn't count. Yeah. Then, starting from A of index 1, 2, 3, ... and n minus 1. So for each of the remaining element, we count once. Okay? Then the number here, n minus 1 numbers. Okay? Yeah. Because 0, we skip it. Yeah. We do not count it. So that's why we have n minus 1. Yeah. All right. Here, we have another chance. We review our counting by reference. Remember? So that method, I hope you try to practice. Yeah. Here we use this counting by reference technique. Yeah. So how do you see it? Yeah. Counting by reference, because this one is assignment operation. So we do not count. Okay. All right. After that, then, each of the remaining element, there we can count. Yeah. So we need to establish 1-to-1 correspondence. Yeah. Each comparison, that's our object 1, right? Object 1, object 2. Object 2, one element in the array, but the array index should be greater or equal to 1. Starting from 1, then we have the 1-to-1 correspondence. Yeah. All right. So there we can easily see the answer should be n minus 1. Okay? Yeah. So very simple, but we need to practice. Especially you need to connect to this counting by reference technique. Yeah. All right. Next, now we need to look at the optimality issue. Yeah. So the question is it possible to further improve the algorithm? Yeah. So after we find the answer, so the first thing you need to ask yourselves, is it possible we can get a better solution, right? Yeah. So here we have two options. Yeah. The first option, improve the algorithm. Yeah. But many times you may not be able to improve the algorithm. Yeah. So although you try very hard, but you cannot do it. Yeah. Well, so in that situation, you may need to consider the second option. Your algorithm, there is a possibility that your algorithm is already optimal. So if you feel your algorithm is already optimal, then you can take this option. You may need to convince people that this algorithm is already optimal. Yeah. Yeah. So that's the optimality issue. Yeah. So here, first, we want to try, is it possible then we can try to improve our algorithm to reduce the comparison number from n-1 to n-2. Yeah. It looks pretty hard, right? Yeah. Based on our detailed steps in the algorithm, it looks very hard to reduce. Yeah. So then our next option, we may consider if this algorithm, this solution is already optimal. Yeah. So, but if we feel it is optimal, you need to convince people. You need to rigorously prove that this solution is already optimal. Okay? Yeah. So here, let's do that. Yeah. So for the post-solution thinking, yeah. The first thing we should try to improve. Yeah. All right. If we cannot, then we need to think about the optimality issue here. Yeah. All right. Yeah. So let's work on this optimality thing. Yeah. The hard part, because to show your algorithm is optimal, in general, it is very hard. Yeah. It is very hard. Yeah. But our question is very simple. For this question, it is not very hard. Yeah. But in the general situation, this optimality step is very hard. Yeah. All right. Here, what do we need to do among all the possible algorithms, how to show that this one is optimal? Yeah. So you can think about how hard it is, because you need to consider all the possible algorithms solving this particular problem. Okay? You need to cover all the possible algorithms. Is that hard? Is that possible? Right? Yeah. Because all the possible, including unknown algorithms. Yeah. Yeah. Because many of those possible algorithms, they are unknown. We do not know the details of those algorithms. How do you cover unknown algorithms? Right? Yeah. Yeah. All right. So the question, how do you study unknown algorithms? That's the hard part. Yeah. All right. Another question, is it possible to study unknown algorithms? You do not know the details, or most of the details of those algorithms are unknown. Yeah. You may know some partial information. Although those algorithms are unknown, but we may know some partial information, right? Yeah? Because from the given computing problem, our problem 5, finding the minimum, at least we know some partial information, right? Yeah. But most part of the detailed information is unknown. Yeah. But we need to study. Okay? We still need to study those unknown algorithms. Is it possible? Okay? Yeah. All right. The answer is yes, it is possible. We can study. We can study unknown algorithm. Yeah. You may wonder why, right? How can you study unknown algorithms, right? Yeah. So here, the idea is very simple. You can study unknown algorithms. Yeah. All right, the basic idea is like this. Yeah. Discover some common property or properties for all those algorithms. Yeah. Common properties. Yeah. Can you discover some common properties? Yeah. Although the details of those algorithms are unknown, but those unknown algorithms should satisfy some common properties. If you can discover those common properties satisfied by all those unknown algorithms, then you can use those properties, common properties, to study all those algorithms. That's the basic idea. Yeah. So our next question, can we find some common property or properties? Yes. Multiple properties, several properties, yeah, satisfied by all those algorithms that can solve this minimum problem. Yeah. So we try to do it. Yeah. All right. Okay. All right. Next, yeah. How to convince people that our algorithms is optimal. Yeah. All right. We need some imagination based on our real-world experience. Yeah. So here, in problem solving, we need to take specific views, right? Yeah. So we need to take appropriate views to understand the problem. Yeah. And if you choose a good view, then you can understand the problem better. Yeah. If you choose some bad view, then you cannot see the inside. Remember? So that's we learned in our previous lectures. Yeah. So we need to take a good view on this problem. Yeah. All right. So let me. All right. Okay. Yeah. So here, in problem solving, your background knowledge also important. Yeah. Your background knowledge. You rely on your background knowledge to solve the real world problems. The more background knowledge you have, the better you can solve the real world problems. Okay? Yeah. All right. So here, the background knowledge we need to use to help us understand this question. So it's very common. So everyone has that experience. Yeah. So that's, playing sports game. Okay? Yeah. So playing sports game, that situation. Yeah. Because we want to use that experience to help us understand the comparison results. Yeah. Understanding the comparison results. When we do comparisons, we have different results, right? Yeah. So here we can use the, people playing games, playing matches. So each match corresponds to one comparison, yeah, between two players. Yeah. Then the results, possible results, yeah. So we do, the connection like this. If the comparison gives us less than result, A less than B, yeah, then we can say it's a win. We treat it as a win in the result of the match. Why? Less than we treat as a win because our goal is minimum, right? Minimum tells us the smaller the better, right? So when we look for solution in this problem, the smaller the element, the better, the closer to the solution. Yeah. So the smaller the better. Yeah. So then, in the comparison, the smaller one we treat it as a winner. Yeah. Because we want to select the one with smaller value here. That's why. So less than tells us, yeah, A less than B tells us A gets a win. Yeah. Yeah. Equal, tie, yeah. Greater than it's a loss. Okay, A loses to B, yeah, greater than, yeah. So in this way, then we can use our experience, our familiarity in the typical sports games to help us understand the comparison results. Yeah. All right, but when we do comparisons, we use the algebraic properties, right? Yeah, that algebraic properties usually not available in our real world sports games. We don't have those algebraic properties. Specifically, we need to use the transitivity property of the inequalities. Yeah, inequalities should satisfy the transitivity property. So what's that? Yeah, it's like this: PA greater than PB. Okay, so player A greater than player B. Yeah, and PB greater than PC. Yeah, if we have these two inequalities, then we have, yeah, it implies, so these two inequalities imply PA greater than PC. That's the transitivity property. Yeah. Yeah. All right. But in our sports games, we don't have that, right? In our sports games, player A beats player B and the player B beats player C. You cannot say player A automatically beats player C, right? Yeah. So we don't have those rules in our typical sports games. Yeah. Yeah. But here, we need to modify the rules. Okay? Yeah, because we do not do the real world sports games. So we use the environment, a real world sports game, that kind of environment to help us understand the comparison results. So we should add this transitivity property in our, discussion. Yeah. All right. Then, if we add this transitivity property, then we allow indirect comparisons. Yeah. So then there are indirect comparisons. Yeah. So what's the indirect comparisons? Yeah. Here, PA greater than PB, that's direct comparison, right? Yeah. PB greater than PC, that's another direct comparison. And between PA and PC, no direct comparison. Well, because we do not do direct comparison between PA and PC. But by the transitivity property, we know PA already beats PC by transitivity. Yeah. For this kind of comparison, we call it indirect comparison because they're not direct. Okay? Indirect comparison also, it is a valid comparison. It is valid. It is legal. Yeah. We can use that. Indirect comparisons. Okay? So based on this understanding, then we can do our discussion. We can do our optimality arguments. Yeah. Because we need to convince people. We need to make rigorous arguments to convince people. Our current solution is optimal. Yeah. All right? Then, now let me show you the convincing arguments. Yeah. All right. So let me make my statements one by one in a sequence. Yeah. So you follow my logic. Yeah. All right. The first statement. Yeah. All right. So that's the setup. Okay. Imagine. So Ming is the final winner. Yeah. Okay. Yeah. Final winner. So that player should beat all the other players. Yeah. All right. Yeah. In comparisons. Yeah. So that the minimum is the final winner. Yeah. All right, so that's our first sentence. Yeah. Next one, it needs to beat all the other elements in the array through comparisons directly or indirectly. That's important. Yeah. We include the indirect way comparison. Yeah. That's the modification we need to add to the real world sports games. Yeah. Indirect comparisons. Okay, all right. Yeah. Then our third sentence statement. Yeah. If an element loses once, then it is eliminated. Yeah. It is eliminated. That means it cannot be considered as the final winner, right? Yeah. Because if one element loses once, then that element is not qualified for the final winner, right? That's obvious. Okay, loses once. Yeah. You cannot. It cannot be the minimum of the whole array. Yeah. Yeah. So this third statement also correct. Yeah. Next one. Each comparison can only eliminate one element. Yeah. Think about this statement. Correct or not? Each comparison can only eliminate one element, not two. Yeah. Yeah. Not two. Yeah. Zach, I saw you. Yeah. I can add you in the break time. Yeah. Yeah. All right. So each comparison can only eliminate one player, not two, not both. Think about it. Yeah. After one game, yeah. After one game, both players are eliminated. That's ridiculous, right? Yeah. Because the winner of that game should not be eliminated. Yeah. The loser of that game should be eliminated. The winner can move to the next round, right? So you cannot say after one game both players are eliminated. Yeah. But actually here I want to make some comment. Actually, in the real world situation, that's possible, right? In a real world tournament situation, it's possible after one game both teams or both players teams are eliminated. Yeah. Like a World Cup. Yeah. Like the World Cup. Yeah. You know, because people calculate the scores, you know, the total scores. Yeah. So they need to compare. So each team, when look at the total scores after one game, so both teams are eliminated. So that's possible. Yeah. But here we do not go there. Yeah. Because the real world situation is very complicated, much more complicated than our current situation. Yeah. Our current situation is very simple, just comparison. Okay. Bigger, smaller. Yeah. So it's not so we do not try to get to the complexity of the real world games. Yeah. All right. So here in our current situation, each comparison can only eliminate one element. The loser is eliminated. The winner cannot be eliminated. Okay? Yeah. All right. But there is a possibility. No elimination. There is a possibility. So that's why we modify the statements a little more here. Eliminate at most one element. There is a possibility both players. So here, the question. Yeah. So you may feel the loser should always be eliminated, right? There is no chance the losers is not eliminated. The losers can move to the next round. Ridiculous, right? Yeah. Yeah, correct. If you think in that way, correct. But the question is, that loser is already eliminated in the previous round. That's possible, right? Yeah? Yeah. So here, let me explain that. So here, the situation is, so you do one comparison, A greater than B, okay? B is the loser, yeah. So we know this B must be eliminated. The question is, you may not add a new element to be eliminated because this B actually, it is eliminated before you do the comparison. Eliminated before, okay? Before you do comparison, it is already eliminated. Why I include this case? Because when people design an algorithm, sometimes people design some bad algorithms. Remember, we consider all the possible algorithms, right? Yeah, because we want to cover all the possible algorithms. All the possible algorithms should include large number of bad algorithms, right? Yeah. Some bad algorithms, although they already got information, this B already eliminated, but the designer, the algorithm designers, they forget to remove those losers, so they keep the losers in the game. Then, they still play some unnecessary game. Yeah. Because you do not need to compare A and B. Okay? Yeah. You already know B has been eliminated. But the algorithm designers, they do not design the algorithm efficiently. Okay? So they keep the losers. Then they need to do redundant comparisons. If they do redundant comparisons, then after one comparison, they do not add any new element eliminated. That's the point. Okay? So that's why we say at most one. It could be zero, yeah, because you do some redundant comparison. So you do not add a new information to your solution. Okay? Yeah. So that's the point. All right. So if we are searching for the minimum, wouldn't yeah. So here for your question, yeah. So we do not keep. Yeah. So when you search minimum, remember, yeah. After one comparison, if the value of the current element does not beat the value stored in the main variable, then we pass it. That means we eliminate it, right? Yeah. So for that algorithm, we do not do redundant comparison. Okay. For the algorithm we discussed before, there is no redundant comparison. So we're fine. Okay. So here I'm talking about the general situation. Yeah. Because we need to cover all the possible algorithms, right? And there is a possibility, that there are some garbage algorithms. Yeah. They may do some bad operations. So here, I'm talking about those, yeah. So not our current, right? Not our current is perfect, okay? Our current solution is perfect. Nothing is wrong, yeah. Yeah, all right, yeah, just some, because here, we want to consider all the factors. We don't want to miss anything, okay? Because in order to try to convince people, each of your statements must be very rigorous, okay? Very rigorous. For example, so here I'm talking about this, our statement number 4. If I say each comparison can only eliminate one, then people may argue there is a possibility it does not eliminate one. Okay? Yeah. Because you do some redundant comparison. So your redundant comparison does not add any new information to your solution. So here, we try to make this statement very rigorous. Okay, that's the point. Okay, yeah, all right, yeah, let's continue. Yeah. Then, our final statement, yeah, our conclusion. Yeah. Because in order to get the final winner, we need to eliminate n-1 elements, right? Yeah. How do you convince people the one you select, that is the final winner? Yeah. So you need to tell people, so this one eliminates n-1 other elements in the array. Yeah. Okay, yeah. But to do that, n-1, yeah, because each comparison can only contribute at the most 1, 0 or 1, not more than 1, right? Each comparison can only contribute at the most 1. But here you need to eliminate n-1. Do you need at least n-1 comparisons? Right? So that's the point. Yeah. 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 So the maximum number of players eliminated by one comparison is 1, at the most 1, 0 or 1. Okay? Yeah. All right. But that 1, yeah, that 1, you need to accumulate those 1s n-1 times, right? So you need at least n-1 comparisons. Yeah. You could do more than n-1 comparisons, but you cannot do fewer than n-1 comparisons. That's the point of the last statement. Okay? For example, if you say you can use n-2 comparisons to find a solution, yeah, but we know this, your n-2 comparisons can only eliminate n-2 elements, right? Still shorter than the n-1 comparisons, n-1 elements, right? Because your goal is n-1 elements. But your n-2 comparisons can give you at most n-2 elements to be eliminated. So you couldn't find one that beats all the remaining n-1 elements from n-2 comparisons. So that's the final statement. Yeah. So after that, now we are convinced. Yeah. So people are convinced. Yeah. So your algorithm is optimal. Yeah. Nobody can do better than this n-1 comparisons to find the minimum. Nobody. Okay? Nobody. Yeah. All right. So here. Yeah. Any question? Yeah. So we finish this optimality proof. Yeah. So any question? Do you feel you are convinced? Yeah. All right? Yeah. Yeah. All right. So then, yeah. So let's try to understand. Yeah. Another level, try to understand. So nobody can do better than this n-1 comparisons in finding the minimum. Yeah. So here, what do you mean nobody? Okay, can you elaborate this, the exact, more specific meaning of nobody here? Yeah. So most specific meaning of the nobody here? Yeah. Yeah. So here, let me ask you, try to elaborate the meaning of this nobody here. Yeah. What is this nobody? Do you mean the nobody in our state, or nobody in our country, or nobody in the whole world, right? Nobody in the whole world, right? Nobody on earth, or nobody, yeah. Another meaning for this nobody is, yeah. So when we say nobody on earth, yeah, usually we mean nobody that are, those people who are living in the world, right? Yeah. Currently, so, they are alive, those people, right? Can we include people in our future generations after 100, 200, 500 years? Some people could find better solution. Yeah. Right? Yeah. Future generations. Yeah. Yeah. Because in science, many tough problems that we cannot solve in our current generation, then after several generations, then, some smart scientists, they can solve, right? They can do better, right? Yeah. So that's very common. Yeah. Here we say our current solution is optimal. Do we mean after 500 years it is still optimal? Still, nobody, even after 500 years, nobody can do better than this n-1 comparisons. That's the question, okay? Yeah. Yeah. The answer is yes. Yeah. Yeah. Nobody can improve. Yeah. So even after, any number of years, so nobody can improve. Because that's the meaning of optimality, right? Yeah. If after 500 years someone can improve it, can reduce this comparison number by 1, then we cannot say it's optimal, right? Then our claim is wrong. Yeah. Right? Our proof is wrong, right? Yeah. All right? So that's the discussion. Okay? All right. So I want to stop the discussion of this topic. Yeah. All right. Yeah. Try to understand. Try your best to understand all these arguments. Yeah. Because you may see many such questions in your quizzes or in your homework assignments or in your tests regarding the optimality understanding. Okay? Yeah. Yeah. Because I may ask you, after several generations, yeah, if the solution can be improved, I may ask you a question like that. Okay? Yeah. D.2, next question. Finding the maximum and the minimum. In this, it's an application, yeah, because we want to apply our solution from D.1 to solve this new question. Yeah. So it's an application of our previous result to find maximum and the minimum. Yeah. All right. First, let me give you the question. We are given an array with n distinct elements. How to find both the maximum and the minimum simultaneously? Yeah. All right. Here I need to explain this simultaneously. Yeah, because some students ask me, so what do you mean? What's your interpretation of the word simultaneously here? Yeah. So let me clarify a little bit. All right. So here you need to design some one algorithm solving this problem. Yeah. After you find this algorithm, so then you write a program to execute this function. So you write a function, find the solution. Yeah. So what you need to do is you need to run your program once, one run. One run, you find both maximum and minimum. Okay? Yeah. So that's the simultaneously. One run. Yeah. Not two runs. Yeah. Because here I do not want you to understand in this way. So you write one function to solve, one function. Then you run your function the first time, you produce the maximum, second time produce minimum. Then you do two runs. Okay? Not one run, two runs. Yeah. Yeah. Not that. Yeah. So you need to run your algorithm once to generate both maximum and minimum. So that's the meaning. Okay? Yeah. And here we want to do that, but remember, we need to find the best solution. Yeah. Because finding the solution, that's not hard. Okay? Yeah. I believe, each of you, every one of you can find a solution. Yeah. But the harder part is finding the best solution. That is hard. Okay? Yeah. All right, so we need to do some analysis. Yeah. First, we need to know our data. Yeah. Here, yeah. Our data. N elements in the array. That's our data. Yeah. Then, before we do our work, let us review elimination method. Yeah. Elimination method. Yeah. When certain elements do not satisfy the criteria, yeah, because when we work on our data, we need to do certain number of comparisons, right? After a few comparisons, if you know some of the elements cannot be the maximum, then you do not need to consider them when you determine maximum, right? Yeah. If you know some of the elements cannot be the minimum, then when you work on the minimum, you should not include those elements that have no chance to be the minimum. Yeah. So that's what we mean, satisfy some criteria. Okay? Yeah. Maximum criteria or minimum criteria, and so on. Yeah. When certain elements do not satisfy the criteria, we can eliminate them from the consideration. Yeah. That's an elimination method. It's simple, right? Yeah, it's simple, it is straightforward, yeah. But it is very important. It is very effective. Yeah. And many people, many students, if they do not have the experience about this elimination methods, it's very likely they keep those elements. They do not eliminate. They keep those elements. Then it's very likely they may do redundant comparisons. Yeah. Remember we talked about redundant comparison in a previous slide, right? Yeah. When your algorithm is not efficient, yeah, designed poorly, then you may include some unnecessary elements, right? Yeah. Then it's very likely you may do redundant comparisons. Yeah. So here, elimination method tells us eliminate those irrelevant elements. Yeah. We only keep the elements that have chance to meet the criteria. Then we keep. Yeah. All right. So this one, the reason we do it in this way, one is there is a reason behind it. So that is it. Since the data size is reduced, yeah, because after you eliminate certain number of elements, the data size is reduced. Yeah. If we work on the data with a smaller size, yeah, here the data size in this one, the data size, because there are n elements, so the data size here is n elements. Yeah. After we eliminate some of the elements, then we reduce the data size. Okay, the data size becomes smaller. Yeah. All right. Yeah. There, we can achieve better efficiency. Better efficiency. Okay. Yeah. All right. Yeah. Now here, some simple notation. Yeah. Because sometimes we do not want to write a lot of words when we discuss our ideas. Yeah. So we may like to use some simple notations. Yeah. For example, comparison. So we use a pair of, parentheses around two elements. Yeah. And this arrow gave us the winner. Yeah. After the comparison, we get the winner. Yeah. Yeah. The notation, simple notation like that. Yeah. But the winner, yeah, then how to define your winner? Yeah. Sometimes the smaller one could be the winner, right? Sometimes the larger one could be the winner. Yeah. But based on our intuition, usually we like to choose the larger one to be the winner. Yeah. Because the smaller one to be the winner, we may get confused. It is very easy to get confused if we make the smaller one to be the winner. Yeah. Yeah. So in our exercise questions, so in general, we want to make the larger one to be the winner. Yeah. Not the smaller one to be the winner. Okay. Yeah. All right. Yeah. But in special situation, then we can make the smaller one to be a winner. Yeah. If it is really necessary. Yeah. Otherwise, because we want to avoid confusion. Yeah. All right. Next, yeah. So another thing, yeah. So here, because we use this data size concept, yeah. How to understand this data size concept? I want to say a few words about this data size. Yeah. In our question, our data is an array. When our data is an array, the data size is the number of elements in the array. Yeah. But there is another possibility for the data size. Yeah. The understanding of the data size, not always the number of elements in the array. Yeah. There is another case we also need to include for the data size. Okay. There is another case, yeah, here. Let me write a second case for this data size. The second case, when we work on our data, the data is only one number. Yeah. The second case, our data is only one number. Yeah. Because we're only given one number, we need to work on that one number. So one number, that data size is not one. That data size is the magnitude of the number. The magnitude of the value, how large it is. That's the data size, okay? Yeah, so that's the second case, the magnitude of the number. Yeah. Here, let me give you an example. Yeah. So actually, you have a simple example, okay? Yeah. So here, let me show you an example. Remember, in our previous lecture, yeah, we do prime factorization. Prime factorization. when we do prime factorization, we do prime factor on one number n, right? Yeah. So that one number n, that's the data size. That n, how large is that n? That's the data size, the magnitude. Yeah. That's the data size. Yeah. When we work on a huge number, the n is very large, the huge number, only one number, but it is extremely large. That means its data size is very large. Yeah. So in that situation, it's the magnitude, not number of elements. Yeah. All right. So, yeah. All right. Yeah. Next, yeah. Details of data manipulation. So now we need to manipulate our data. How do we organize our data for comparisons? We need to do comparisons, but we don't want to do random comparisons, right? Because when you do random comparisons, the useful information you derived, it's very hard to organize the derived information. Okay? Yeah. So then it is very messy. If you do not organize your results, your data, your results well, then you may do a lot of redundant comparisons. Okay? So here we want to organize our data well. So the goal is we want to avoid redundant comparisons. Yeah. But how to do that? Yeah. All right. Group the data in pairs. Yeah. So that's one commonly used method, in pairs. Okay? Yeah. The first two elements, we group them in the first pair. Next two elements, we group them in the second pair, and so on. Okay? Yeah, so yeah, keep doing. Yeah. Yeah. But sometimes we may not be able to group all of them in pairs, right? Yeah? Because if we get an odd number of elements, then the last element cannot be assigned into any pair. Yeah. Yeah. Odd case. Even case, that we can group all the elements in pairs, but odd we cannot. Okay, all right. Yeah. So next, then we have the situation. Yeah. So we need to consider two cases. Yeah. This n, even case or odd case. There are two cases we need to consider. Yeah. Even case or odd case. Yeah. Two cases. Yeah. All right. So here there is a simple strategy in problem solving. Yeah. When we have several cases to be considered for a problem, yeah, what is the best way to work? Yeah. So the best way, yeah. So we always work on the simplest case first. Simplest case, yeah. Not the hardest case, yeah. Yeah. People, so you know, from the people's experience. So I think most of you have this kind of experience. When you work on some relatively hard thing, you want to start from relatively easier part first, right? Not the harder part, okay? Yeah. So that's the, most people take that strategy. Yeah. That's the right strategy, okay? Always work on the simplest case first. And this strategy actually is very effective. If you do this way, then your success rate will be higher. Yeah. Yeah. Will be higher. Yeah. All right. The reason is this. Yeah. When we solve general computing problems, experience very important. experience. Okay? Yeah. Our experience, very important. All right. Now, when we work on simplest or easiest case first, the difficulty is smaller, right? Yeah. Easier to solve, difficulty is smaller. Okay? Other than that, we build up our experience. When you solve simplest cases, you collect, you build up your experience. Then, after that, when you move to harder cases, you already have experience. Okay? You already have some partial results. Yeah. Here I want to say partial results. So you can use your partial results to help you to do better work. Yeah. So that's the idea. So we build up. Okay? Yeah. Here, we take that strategy. Yeah. So for that strategy, even case, odd case, which one do you feel easier? Then we should work on it first. Even case easier or odd case easier? Anyone? If I ask you to solve this problem, do you want to start with even case first or odd case first? Even, yes. Yeah, because even you have all the pairs. Yeah. You don't need to consider the singleton case, right? The odd case, there is one singleton case. Okay? Yeah. So when you work on the even case, then you have all the pairs. Okay? No singleton. Yeah. No special singleton case to be considered. Then it's simpler. Yeah? Yeah. That's correct. Okay? All right. All right, let's